This is my second video in my module on graphing inequalities, and in this video we're going to focus on actually systems of inequalities, not just sketching inequalities, but systems of inequalities. Okay, so we're going to start by reviewing a few concepts just really quickly. When we say a system, what we're referring to is more than one, say, equation or inequality, and what we're looking for are common solutions to all, let's say, constraints in the system. You know, we're going to be using this word in the future anyways, but constraints, about why we use this word, but all, say, like arguments in the system, we want to make them all true. So like what points in the graphing plane here would make everybody here happy. And so what we need to do is actually graph the equations that are associated with these inequalities first, and then do their corresponding shading. But what we're looking for is all the points x, y, that when I plug it back into each makes them true. Well, if you think about the graph of an inequality, we're talking about shaded regions. So we're looking for where all these regions would be shaded together, okay? And not only that, as kind of practice for the future here, what we're also looking for are any vertices of the shaded region. So we're going to talk about, going ahead and constructing this, but why we need the vertices, why we'd want the vertices, and what we call the region itself. So let's go ahead and start with this first constraint here, or inequality. It says x minus y is less than 2, okay? Just as a matter of doing this very quickly, you'll notice it's in standard form. It's not, in this case, worth my time to actually put this into slope-intercept form. And also, you'll notice here, if you do put it in slope-intercept form, you're going to have to divide by a negative anyways, which means you're going to have to remember to switch this inequality sign. So it's probably best to just go ahead and graph it as standard. And the best way to do so is just go ahead and find its intercept. So we look at this and we say, well, let's plug in 0 for x, let's plug in 0 for y. What would our x and y values be, or y and x values be respectively here? So if I plugged in, say, 0 for x in this first equation, I would have just negative y equals 2 for assuming an equation. So let's see, 0 minus y, and we'll go with equals 2 here. Then that would mean y equals negative 2. In other words, it hits my y-axis at negative 2. And if we were to plug in 0 now for y, plug that in, we'd get x minus 0 equals 2. In other words, x equals 2. So when y is 0, my x value would be 2. These are the intercepts of the first inequality. So we're going to go ahead and put these up on our graph up here. We say 0, negative 2. It hit my y-axis at negative 2. And it hit my x-axis at 2, 0. And then we need to go ahead and connect these dots. It is a line. So the question is, should I connect it with a solid or a dotted line? You'll notice here that it is not less than or equal to. It's just less than. So we're going to go ahead and connect these out with just a dotted line here. And this is very important. We want to get into this habit. But we're going to go ahead and label this with its equation. So we're going to say x minus y equals 2. We want equals, okay? When we just graph the boundary line, we'll write equals. So we'll go ahead and leave this for now. I know we need to do the shading, but I'm going to leave it, okay? And we'll come back and do it later. Now our next constraint is x is greater than 2, okay? This is a vertical line. If we were to graph x equals 2, the associated equation, have a vertical line at 2, and it would also be dotted. So we say, okay, so we have this dotted dashed line, and this is at x equals 2. Go ahead and label this x equals 2. Come back and graph it or shade it again later, and we say y less than or equal to 3. So we say, well, this is a horizontal line. We'll graph the associated equation y equals 3, and this would be a solid line. And the reason why is because it is not just less than, it is less than or equal to. Okay, so we get this line right here. We can go ahead and hit y equals 3 on there. Now we are going to go back and do the shading here. The thing is, go ahead and get the boundary lines here out of the way and do the shading next. Remember, to shade, we're shading the side of the inequality that contains all of its solutions. And remember, a solution is any point that when you insert it back into the original argument would give you a valid statement. So for example, with x minus y is less than 2, we say that's this constraint here. I've already labeled this. We're going to choose a point not on this constraint. And so 0, 0 is always a very good candidate. If 0, 0 is not on the constraint, let's test it. And so we'd have this statement here. We say, all right, well, x minus y is less than 2, or we're plugging in 0 for x and 0 for y if I'm testing this point 0, 0. And I get the statement 0 is less than 2. And since this is a true statement, we are going to shade toward the side of this constraint that contains the point 0, 0. So you're going to be seeing me do this. I'm going to say, well, I'm going to shade to this side here. I mean, I could just go ahead and scribble in the entire half plane here, but you might see how that would just kind of pollute the area. You wouldn't be able to, see what's going on with your other two constraints. We're saying, okay, so we're shading kind of the top left of this constraint here. The other two constraints, so we say x is greater than 2. That's this, boundary line here. I'll be real honest with you, if you said shade the side that contains all the points where x is greater than 2, I already feel that I'm going to be shading towards the right. But just to kind of prove this here, what we would do is we could still test the point. We say 0, 0. 0, 0 is not, also not on this constraint. We could test that. We could say, all right, well, x is greater than 2, where we're plugging in for x a 0, and there's no y to plug into. So I get this statement 0 is greater than 2. And so we end up with this false statement. This is false. And so the thing is, with this vertical constraint here, if 0, 0 is false, I'm not going to shade towards the left, because if 0, 0 is false, all the points over here are false. So we're going to say, all right, well, actually, I would shade toward the side containing its solutions, which is actually this side over here. We'll just put in all of our arrows here. Okay, so we say arrows. So far, if you said, well, where is everybody shading together at? We say it's this little V-like portion up here. Now we just need to decide, are we going to shade above or below this y equals 3 line here? So we say our original constraint or argument here was y is less than or equal to 3. Again, for something like this, you say, well, y is less than or equal to 3. That'd be all the points below this line is what it would be. I mean, those are the y values less than or equal to 3. But also this, we could say testing 0, 0, which is clearly underneath it. If I were to plug that in, we say, okay, so y is less than or equal to 3. We get this. We say less than or equal to 3. We'll plug in a 0. We get 0 is less than or equal to 3. And this is true. And so since this is true, since 0, 0 is true, and it's below this line, we also want to shade all points below this line. And so now what we're looking for are a few things here. So let's start with a few vocab terms. What we're looking for is the region that all of these 3 inequalities have in common, because we are looking for the solution region to a system. And to a system, it means we need all the points that make all 3 or all of them true at the same time. So this would be where all the arrows shade together. And so what we see here is this. We get this little area right here. I don't know if you can see, is this little triangular region, okay, right here. Okay, and this region has a name. We're going to refer to this as the feasible region. The feasible region, when you say something is feasible, it's like doable, okay? It's like it could potentially be something that works. And so the reason why we refer to this triangular region as the feasible region is because this is the region where if I were to select a point out of it and insert it back into any of the original constraints, I would get a valid statement. So all of these points would be feasible with this system right here. Another thing I want to say about this feasible region is that it is bounded. Okay, so this is a bounded feasible region. You think about the word bounded, it means like surrounded on all sides. Okay, let's say for instance here, and I could pull out a different color if we pull out like a green. If we had shaded above, like this feasible region, we would have been in this area kind of up in here. Okay, and this would have been something that would have had a set of solutions that goes on forever and ever, up in this direction. We'd say this would be like unbounded. Okay. And so we do want to distinguish between bounded and unbounded. And last but not least, what we want to do is we want to find the vertices of this feasible region. So again, we'll switch out the color again here. We say maybe like a golden color here. The vertices of the feasible region, that would be points like this. Oops, sorry, I said golden here. This point, and this point. Okay, so we are often interested in finding these vertices of the feasible region. Well, I'll tell you what, a couple of these are really kind of easy to determine. So for example, this point right here is clearly, because of intercepts, and what I know is this is the point, we'll put in a darker color here. This is the point, go back to my kind of pinkish here. This is the point 2, 0. We established this earlier. So we say vertices. We're interested in finding the vertices of the feasible region. We have the point 2, 0 is 1. We also have this point here. This seems clearly to me to be the intersection of the line x equals 2 and y equals 3. So this would be the point 2, 3. Okay. The last point here, we talk about graphing method. Trying to determine what this point here is, just eyeballing it. Honestly, I'm fairly confident this is the point 1, 2, 3, 4, over 5, up 3, but let's say I don't know what this point is. The reason why we had labeled these constraints in the first place, that is, put the equations on their graphs or their boundary lines, is because, well, if I wanted to find where 2 things necessarily intersect, what we could do is we could solve a system of equations to find the common point between the two. So we know we have this, we say x minus y equals 2, and then that equation ran into this horizontal equation here, y equals 3. And you can see, well, if I said go solve this system of equations, well, we already know the y value of this system. We'd say 3. And in order to find the x value, we just go substitution method. We'll go plug this back in up here. So we say x minus blank equals 2, where the y is 3. So we x is 5. So I verified that this indeed is the point 5, 3. 5, 3. Okay, so we're interested in these vertices of this feasible region. We're going to try this again very, very quickly here, but with non-linear constraints. We have a linear and a non-linear. So actually, let's go ahead and start with our steps here. Number one is graph the equations. Graph the equations associated with the constraints here. So we say, all right, well, if I was going to graph x squared minus y is less than or equal to 1, honestly, what we do is just x squared minus y equals 1 and go graph this. And so let's see, well, negative y would equal negative x squared plus 1. And if I were to multiply everything by a negative 1 now, we'd say, okay, well, x squared minus 1 is my graph. So this is our parabola that's been shifted down 1. So I'll go down 1 here from the origin. It's got an a value of 1, so go up 1, right 1, up 1, left 1. We notice it's less than or equal to, so I can go ahead and give it a solid line boundary here. And we will shade in a moment here, but we're going to label this. This is the graph y equals x squared minus 1. We could also, label this x squared minus y equals 1. It's entirely up to us. The next graph here, I notice this is a linear constraint, so we would graph, the equation negative x plus y equals 1. We go with the equation here. And I say, since it's in standard form, we're going to find its intercepts. Plug in 0 for y, plug in 0 for x. If you plug in, 0 for x, you'd get the statement here, y equals 1. So it hits my y-axis at 1. If you plug in a 0 for y, the y term would disappear. We get negative x equals 1. So positive x would be a negative 1. So this would be a negative 1. So it's going to hit our x-axis at negative 1. So negative 1. So that's this point here. We could overlap it there. And it hits our y-axis at 1. So it'll be this right here. And we say, do we want a solid or dotted line? Well, notice again, it's less than or equal to. So we're going to go with a solid line. So as nicely as I can, I'm going to make this constraint here by hand. We're going to say, okay, label this. So we get negative x plus y equals 1. Okay, so now we've graphed the equations. Step 2, we are going to test points and shade. Test points and shade. We want to find the common region, the point or the region where they all shade together, the feasible region. So, we say 0, 0 is on neither of these graphs. We could go ahead and test 0, 0 into both of our original constraints. Starting with the first one here, which was x squared minus y. It's less than or equal to 1, or we're testing 0 to 0, 0 to see if it makes a valid statement. So we get 0 is less than or equal to 1. This is true. 0 is less than or equal to 1. And so for our parabola here, we're going to shade towards the side of the parabola that contains the point 0, 0. So this would be all points kind of on the inside of this parabola because 0, 0 also lies on the inside of the parabola. Okay, so now we need to test a point on this linear inequality, which was negative x plus y is less than or equal to 1. And we'll test 0, 0 again here. So we'll take out all our x's and y's and put in a 0 and a 0. So we get 0 is less than or equal to 1, which is also true statement. So with the line here, we say 0, 0 lies below it. So we're going to shade below this line here. So we're saying, well, first of all, where would all these arrows shade together at? Where is our feasible region of points? The points would make everybody true. You see that we get this region inside the parabola here and below the line. So this is our nonlinear feasible region here. So it's feasible region. This is the region containing points that would satisfy all constraints in the system. And the next thing we want to find these vertices here. So I don't know, we haven't used an orange in a while. It's orangey, burnt orange. We want to find the vertices of this feasible region, which are these 2 points right here. We would not consider this as a vertex, not a vertex. Weird, it's a vertex of the parabola, but it's not a vertex of the feasible region. So we want to search for these 2 points right here. I say, well, what are these 2 points? To be very, very honest with you, we are pretty much certain that this is the point negative 1, 0. So when we say vertices of our feasible region, we say negative 1, 0 would be a vertex here. Now I'm not sure about this vertex right here. So what we'll do is we'll solve a system of equations. Solve a system of equations, we'll find the points at which the 2 graphs intersect. So we'd say, oh, well, our equations in the first place were, and I'll use the modified first equation. We had y equals x squared minus 1 was in our system. We have negative x plus y equals 1. I suppose we could do substitution method here, or plugging this in for y. So we get negative x plus blank here for our y is 1, where we're inserting now x squared minus 1. So we get this statement. We get x squared minus x minus 1 equals 1. If we subtract 1 from both sides, we end up with this x squared minus x minus 2 equals 1. And when we factor this, we end up with a statement here. We get x let's see, two numbers that multiply out to be a -2 that add up to be a -1 would be -2 and a +1. And setting that equal to 0, it yields two x values here. We say x equals both +2 and a -1, our solution values. So to find the y values associated with these, we'd have to actually like go plug them back in. So we'd say, all right, when x is +2, plug that back in. We say y equals 2 squared minus 1. So we get 4 minus 1 is 3. So we get the point 2, 3, 2, 3. And if we plug in a -1 into this equation, we get, let's see here, y equals -1 squared minus 1. So we get y equals 1 minus 1. So we get y equals 0. So we say, all right, when the x value is -1, we get the point 0 for y. So these right here are the two values for which these graphs have the same point on them. We already determined -1, 0 was this first point where these two graphs collide. But we were able to determine that the other point here is the point 2, 3. And that's what we were after. Cool, man. So yeah, this is systems of inequalities, feasible regions, bounded, unbounded. This is a bounded feasible region, and finding the vertices. Cheers.